Okay, in the last recording we looked at linearizations. Now we're going to look at differentials. If y equals f of x is a differentiable function, then the differential dx is an independent variable, and the differential dy is dy equals f prime of x dx. Now geometrically, the differential dy is the change delta L in the linearization of f when x equals a changes by an amount of dx, or delta x. When dx is a small change in x, the corresponding change in the linearization is precisely dy. Now let's take this example where y is x of f plus 37x, and we want to find dy when x equals 1 and when d of x equals 0.2. Now first let's find dy, and remember we just said that dy is f prime of x dx. That means that dy is f prime, and we take 5 x to the 4th plus 37 times dx. Now we want to find this dy for x equals 1 and dx equals 0.2. So we just plug in those values. So we plug in 1 for x and 0.2 for dx. Well, 1 to the 4th is 1 times 5 is 5. So I have 5 plus 37 times 0.2. 5 plus 37 is 42 times 0.2 gives us 8.4. So dy is 8.4 when x is 1 and dx is 0.2. Now let's look at an application so that we can understand a little bit better what these differentials mean. The radius r of a circle increases from radius equals 10 meters to 10.1 meters. Use dA to estimate the increase in this circle's area A. Estimate the area of the enlarged circle and compare your estimate to the true area. Okay, well we know that the formula for the area of a circle is area equals pi r squared. Now what we want to do is find the differential. So that will be dA equals, and we'll take the derivative of A, which is 2 pi r, and we'll multiply that by dr. Okay, so that tells us our differential dA. Now we're looking at dA here when our radius is 10, and we're changing our radius by 0.1 meters. So we're going from 10 meters to 0.1 meters. So here then, dA would be 2 times pi times 10 meters times our change, which is 0.1. That would be 2 pi square meters, since it's a change in area. Now what that means is that our change in area for this change in radius will be fairly close to 2 pi square meters. What that means is if our area, and this is just an estimation, our area was for radius equals 10, so here's our estimate, 10 squared times pi, or pi 10 squared, and we're going to add 2 pi to that. Okay, so our original area, 10 squared, is 100 times pi is 100 pi for a circle of radius 10. And we're saying that it should increase by about 2 pi, or be somewhere around 102 pi. That is our estimate. This dA tells us that's the change in our area when we change our r by 0.1. Should be approximately 2 pi. Now, it's not actually going to be exactly that. The true area, if we go to 10.1, would be pi times 10.1 squared. Well, if you square 10.1, you will get 102.01. And of course, this should have had meters squared on it also, since we were dealing with area here. But our true area is 102.01 pi meters squared. Our estimated area using differentials was 102 pi meters squared. So we really were not off by very much using this method of estimating using a linearization.